Hello, in this video we will deal with the Nobel Prize in Chemistry from 1913, awarded to Alfred Werner for his work on the linkage of atoms in molecules, especially in organic chemistry. We're going to give some works information and biographical information coming from an official Nobel Prize and also a summary of the award ceremony speech given to Alfred Werner when the prize was handed to him. And in the next video, we'll deal with his own Nobel Prize lecture given by him. First, some works information coming from the official Nobel Prize site. Here you see the link. The world around us consists of molecules that are composed of atoms. Charting the bonds and positions of atoms in space is one of chemistry's fundamental missions. In 1893, Alfred Werner contributed to the understanding of molecular structures of organic substances, chemical compounds that do not contain carbon. According to Werner, the attractive forces are not conserved to certain directions in the atoms, but emanate uniformly from the middle of the atom. With a new coordination number for an atom's bond, he shed light on the structure of the substances. Here you see the periodic table, by the way, containing the different chemical groups. Then we go to some biographical information, also coming from the from the Nobel Prize site, summarized by me. It's not complete, so if you want to read the complete biographical information, you have to follow the link, which you will see later. In 1890, he took his degree in the University of Zurich with a thesis on the spatial relation of the atoms in molecules containing nitrogen. From 1890 until 1891, he did further work on this subject and visited Paris, where he worked under Professor Berthelot at the Collège de France. In 1892, he returned to Zurich as a professor in a technical high school. In 1893, he was appointed associate professor in the University of Zurich to succeed Victor Merz and gave the university lectures on organic chemistry. In 1895, he became, when he was only 29 years old, professor of chemistry in the university, giving the lectures on organic chemistry until in 1902 he took over the lectures on inorganic chemistry as well. In 1895, he was acquired Swiss nationality, and though he was offered posts at Vienna, Beit and Würzburg, he declined these, preferring to remain in Zurich. Werner's game will also be associated with the theory of coordination, which he established, and with his work on the spatial relations of atoms in a molecule, the foundations of which were laid in the work he did when he was only 24 for his doctorate thesis in 1982. In this work, he formulated the idea that in the numerous compounds of trivalent nitrogen, the free valence bonds of the nitrogen atom are directed towards the free corner of a tetrahedron, the four corners of this being occupied by the nitrogen atom. In 1991, he had published a paper on the theory of affinity and valence, in which he substituted for Kekulé's conception of constant valence the idea that affinity is an attractive force exerted from the center of the atom, which acts uniformly towards all the parts of the surface of the atom. In 1893, he stated in a paper on mineral compounds his theory of variable valence, according to which inorganic molecular compounds contain single atoms which act as central nuclei around which are arranged a definite number of atoms, radicals, or other molecules in a simple spatial geometric pattern. The figure which expressed the number of atoms grouped around the central nucleus called by Werner the coordination number. The most important of the coordination numbers being 3, 4, 6, and 8. The number 6 occurring especially often. Thousands of molecular compounds correspond to the number 6 type, and in the majority of these there's a central organ with coordinated atoms at the corner of an octahedron that has 8 corner points, an octahedron. Octa is 8. For the next 20 years, Werner and his collaboration studied and prepared a new series of molecular compounds and studied their configurations, publishing many papers on them, 150 of which were by himself. Finally, his work culminated in the discovery of optically active isomers of the complex studied, the existence of which had been forecast by his hypothesis. Isomers are molecules that have the same configuration number of atoms, but in a different spatial configuration. More than 40 series of active complexes with octahedral symmetry were separated in optically active forms, with the result that the special configuration of the complexes to the coordination number 6 was established as firmly as that of the tetrahedral of Van 't Hoff and Nobel. Tetra is 4. Werner also worked on the complexes with other coordination numbers, especially 4, for which the form can be tetrahedral or a plane square. As Paul Pfeiffer, in his account of Werner's work, published in The Great Chemist in 1986, edited by Eduard Farber, synthesized in New York, remarks the coordination theory of Werner extended throughout the whole range of systematic inorganic chemistry and into organic chemistry as well. For his work on it, Werner was awarded the Nobel Prize for Chemistry for 1913. As you can see, this is a summary. If you want to read the complete biographical information, you have to follow this link. Here you see structures, chemical structures. This is a hexagonal, trigonal, and octahedral, which are also mentioned in the text. If you want to study them, you have to pause the video or go to the Wikipedia page. Here you see isomers. Here you can see, for instance, that cis-butene and trans-butene, if you put the number of hydrogen and carbon atoms, you will see that they are exactly the same, but you see the configuration is different. You see CH3 and CH3, and here you see them. This CH3 is on the same place as this one, but this one is at another place compared to that one. That's called isomerism. As you can see, there are several types. Then further information coming from the award ceremony speech by former Councillor T. Nutstrom, also summarized by me, and the original is also, of course, on the Nobel Prize official site. So if you want to read that, you have to follow this link, which will be shown at the end. The concept of valence, on which all modern chemical theory is based, had been found unable to deal with a large and important group of mainly organic compounds, so-called complex or molecular compounds, because it was unable to provide a satisfactory explanation of their internal structure. By considerably expanding and modifying the former concept of valence, Werner both illuminated the area concerned and opened up new paths for research. By contrast with the conventional view, Werner does not conceive of the binding forces of an atom as being divided into certain units of affinity, determined in number and direction. He considers affinity rather to be a force issuing from the center of the atom, uniformly attractive in all directions, whose geometrical expression is therefore not a given number of guiding lines, but of a spherical surface. Atoms or atom groups which can occur as ions or whose chemical binding capacity is equivalent thereto can enter bonds in the manner previously indicated by means of the so-called primary valences. These do not, however, represent the sum total of affinities. The remaining residual affinities or secondary valences, whose energy content is assumed to be less than that of the primary valences, but which do not otherwise in principle differ from them, brings about bonds with atomic complexes which cannot occur as independent ions, for instance water, ammonia, potassium chloride, etc., and thus make provision for compounds of higher order, so-called addition and intercalculation compounds. The number of atoms or groups of atoms which can be linked in the first sphere with the elementary atom functioning as center, or which in other words can be coordinated into complex under direct linkage with an atom, Werner calls the coordination number. This is a clearly defined numerical concept which is superior to other concept designs to characterize affinity saturation, in that it is to some extent independent of the nature and valence of the interconnected elementary atoms, insofar as it has the same value for the great majority of elements. Only two such numerical variables have been demonstrated as yet, that is 4 for some element and 6 for the others. By this approach, of which only some principal characteristics can be mentioned here, Werner explains the structure of an origin of complex inorganic compounds. By widening and deepening the concept of valence which incorporates his view, he has succeeded in bringing atomistic and molecular compounds together under a common point of view. He has drawn a large number of diverse compounds into the range of his comprehensive experimental work and has thereby been able to establish a uniform system for a large group of inorganic compounds. Werner's approach has also exerted significant influence on research in inorganic chemistry. Werner's theory has been supported in an extremely important and valuable manner by the stereochemical researches which he carried out as a sideline, mostly in connection with his work on the constitution of chemical compounds. By virtue of his theory of the asymmetrical common atom, Van 't Hoff became the real founder of the stereochemistry of organic compounds, and Werner's indisputable merit to have introduced this approach to inorganic chemistry as well. Even in his earlier investigations into certain metal ammonia, he was able to show that numerous cases of isomerism in complex cobalt and platinum compounds could only be satisfactorily explained by steric approach. For complex radicals of a certain type, he put forward a steric theory, the octahedron theory, which predicted that certain of these compounds must occur in two stereoisomeric forms, a prediction which has been confirmed by experiment. By far the greatest interest in this field attaches also to the discovery he made in the last few years that certain cobalt, chromium, iron and radium compounds with an asymmetrical metal atom in a complex radical can be divided into forms which behave like mirror images and show differences of the same kind as those in organic mirror images isomers, that is, they are optical antipodes of each other. The discovery is a splendid support for Werner's theory, and it has been called the most important discovery in chemistry in recent times, and his stereochemical works makes him the founder of inorganic stereochemistry. As to Werner's research work as a whole, we can with good reason agree with the remark of an researcher worker that Werner's theoretical and experimental work in inorganic chemistry has opened new paths of chemical research and is of positively revolutionary significance. Okay, that is a summary of the ceremony speech. If you want to read the complete speech, you have to follow this link, which leads you to the official Nobel Prize site, of course. Here you see again two transbutene and these are the same that we just saw it. You see there are two common atoms with a double bond. One is and each common atom is also linked to a nitrogen and to an H3C. This is the same here, but you can see the position of the CH3 and the H is different. So they have the same formula. There are 4 carbon atoms and 8 hydrogen atoms, and that's the same here too. Thus the formula is C4H8, but they are structurally different. That's called isomerism. Okay, this is it for the moment. Next week we will go into the Nobel Prize lecture given by Alfred Werner. The award speech was given to him, and that's next week, as I said. For now, thank you for watching, and maybe until another time.